The last thing we'll deal with for this lesson is working with definite integrals that involve u-substitution. And where we'll start to work with definite integrals is when we see the integral from a to b of our inside function, identify u, and evaluate du for that u-substitution, just like we did on the initial examples. Our second step will be to convert a and b, the x values for our boundaries on the integral, into u values. This will be the new step and the one we'll investigate more closely when we get into the examples. Finally, we will evaluate the new integral using the fundamental theorem. And key on this, you do not need to substitute the original function back into your expression. When we do definite integrals involving u-substitution, we're going to do all of our substitutions, but not worry about substituting anything back in like we did with the indefinite integrals. And so let's wrap up by seeing how this is going to look in practice. In the first example, we have the integral from 1 to 3 of 2 times the square root of 4x minus 3 dx. Notice that square root of should tell us that our inside function from chain rule was 4x minus 3, and the derivative of that will be 4 dx. Well, we have a 2 dx hanging out outside the square root. We want to make that 2 times bigger. So we'll multiply the inside by 2, put a 1/2 outside, and rewrite this as 1/2 the integral from 1 to 3 of 4 square root of 4x minus 3 dx. And now we can complete our substitution. This will become the integral of square root of u du. But here's where step 2 from the directions above comes into play. 1 and 3 are x values. If we're going to change any part of this to another variable, we need to change every part of it to another variable. And so what we're going to do is we're going to change both boundaries. And we're going to say that we're going to look at, for that top boundary, we actually want to know the u value when x is 3. For the bottom one, we want to know the value for u when x is 1. And we have an expression that will give us u. If we know x, it was at 4x minus 3. So the u value from using an x equal to 3 will be 9. The u value from using an x equal to 1 will be 1. And those will be the boundaries on this brand new integral. And now we'll carry out this problem in the exact same fashion we've done in the past. This will be 1/2. Remind yourself that this was u to the 1/2 here, times u to the 3/2, with the 2/3 out in front, from 1 to 9. And we'll end up with 1/2 my function evaluated at 9 minus that same function evaluated at 1, which will be 9 to the 3/2 is 27 times 2/3 is 18, minus that whole second expression is just 2/3, and our end result will be 26/3. Back to this note I made above, once we've changed everything, including boundaries, to all be in terms of this more simple variable, we don't need to change back to x. The area bounded under this square root of u curve from 1 to 9 is the same as the area bounded under this more complicated looking function from 1 to 3. We've shifted everything in the problem to make it easier. So our final example, the integral from pi over 4 to pi over 2 of cosecant squared x times e to the cotangent x, and seeing e to something, usually a good sign. That exponent will be our inside function, and it works out because the derivative of cotangent is negative cosecant squared of x. Now we don't have that negative sign, so we're going to go ahead and bring one in, put another negative sign on the outside to offset it. I'm also going to want to get u at pi over 2 for my top boundary, u at pi over 4 for my bottom boundary. So cotangent of pi over 2, well, that's just going to be 0, and cotangent of pi over 4 equals 1. And so we will end up with negative integral, and notice how the pi over 2 became the 0, so it's going to look a little backwards. We're going to be going from 1 to 0 of e to the u du. And if you want to, you can leave it this way and evaluate, or that negative, I can just use that to flip my integral and make this the integral from 0 to 1 of e to the u du. Won't matter which step you evaluate from, they're both going to get you the same answer. This will equal the antiderivative of e to the u is e to the u. We're going to evaluate that from 0 to 1, which will be e to the first power minus e to the 0, which will just be e minus 1. Don't need to worry about getting that as a decimal. This is a good exact answer right here. And that will do it for lesson 8.1, this new integration technique, u-substitution. 8.2 will be more of the same, but bring in a couple extra types of functions that we're going to want to be aware of that also involve u-substitution. So you're getting yourself a couple lessons to make sure that we are refining this skill. Please make sure you review and summarize these notes and move on to the practice when you are ready. Thank you for watching.